You hear everything. That's not good. Okay. So let me share my screen. If I forget, you have a quiz. Oh, tomorrow's the 20th. I could just look at my watch. 20th to the 23rd, which is Friday. No. Because tomorrow's Wednesday, 20th. 22nd. Should be the 22nd. Sorry, I was including the 20th. So, okay. So don't forget. Now I will give you, so I will because the quiz is on sections 4.1 to 3. And section 5.1 possibly. So it could be on any of those sections. I'm going to post, and the exam is the following week. So, and the exam includes those chapters and those sections. Then I'm going to post a solution for the quiz on Sunday or Saturday, once you have turned in the quiz. Now, the exam, your second exam is on the 23, 24, 25th to the 29th, if I remember correctly, the dates. Let me check my laptop. Yes, 25th to 29. And that's again going to be on chapters 2, 3, 4. And I already said it's going to be on sections 5.1 to 5.2 only. So whatever sections we do today will not be on the exam. And I'm planning on finishing chapter 5 today, which we're going to do section 5.4 and 5.5. But any questions on that? Yes, no? Just trying to make sure. Okay. So that's what's going to happen this week. So you have a quiz. I gotta clean this. You have a quiz and you have an exam next week. So you have a quiz starting tomorrow. And again, I'm probably going to post a quiz tomorrow or maybe tonight, but it'll be open up tomorrow anytime after like 8 a.m. So just keep that in mind. But it should be up by tomorrow for sure. Okay, now I'm sure some of you already noticed the exams. You know what? I'll talk about that later because some people might come in late. And so then when I say it, they're not here. So I'll talk about that later. Okay. So let's start with section 5.4. Section 5.4. Oops. Okay. Section 5.4. Now, let's go back to something that we've done before. I don't remember exactly what section we did this, but it'll be a good reminder. It was on your last quiz. And what I'm talking about are recursions. So let's say we have a sub 1 or a sub n is equal to a sub n minus 2. 3 times a sub n minus 2 plus, let's say, a sub n minus 1, where a sub 1 is equal to 3. Or let's say a naught is equal to 3, and a sub 1 is equal to 5. Now, we are interested in finding the next term, and we're interested in finding the next term For this recursive algorithm, we are dependent on the last two terms. So let's suppose we want to find a sub 2. If we want to find a sub 2, we have 3 times a sub 0 plus a sub 1. So notice that a sub 2 is dependent on the last two terms, 3 and 5. So a naught is 3, and a sub 5 is 5. A sub 1 is 5, sorry. So 9 plus 5, that's 14. So that's a sub 2. So now I have another term. So if I want to find now a sub 3, then I am dependent on 3 times a sub 1 plus a sub 2. So now I'm dependent on the 2 before a sub 3, which is a sub 2 and a sub 1. So 3 times a sub 1, which is 5, plus a sub 2, which is 14. So that's 15. That's 29. Any questions on that so far? Any questions? No? Okay. If we want to find the next one, which is a sub 4, it is 3 times a sub 2 plus a sub 3. Okay. A sub 2 is 14 plus a sub 3. So these are the new ones I have to find, and where they were dependent on the last two. 3 times 14 is 42 plus 29. So that's going to be what? 6? No, it's not. 71 and so on and so on. So that's going to be 71. And this goes on obviously forever, depending on how many terms you're looking for. But you see what a recursive algorithm is. Does everyone see that? And I believe I gave you something like this on a quiz. Yes, no? Okay. So you understand what it means to be recursive. Where in order to find, another way of looking at it, in order to find the next term, you're dependent on putting it back into the original algorithm, which is this one. Okay. You're not just, it's not like an arithmetic sequence where you just keep adding this and this and this. No. This one is the next term is dependent on the last two terms, which means you have to put it back into the original equation to find the next term, and so on and so on. Now, let's look at factorials. Now, suppose we have n factorial. What does n factorial mean? Well, for those who don't know, n factorial means n times n minus 1 times n minus 2 times blah, 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 times 3 times 2 times 1. So what you're doing is you're taking the product of all those numbers up to n. That's what you're doing. So a quick example of that will be, let's say 5 factorial. 5 factorial will be 5 times 4 times 3 times 2 times 1. So this is going to be 20 times 3 times 2 times 1. Then this is going to be 60 times 2 times 1. And it's going to be 120 times 1, which is just simply 120. That's how factorials work. That's pretty much what you're doing. Good? Okay. So let's suppose we want to write a program for factorial. Let's say we want to write a pseudocode. So let's write a pseudocode for factorials. Here's my procedure. And I'll call this factorial. Now, what's going to be given into this factorial is going to be n, where n represents just non-negative integers. And I should have stated that from here as well. Your n is any integer, but it has to be greater than or equal to 0. Okay, now keep in mind that 0 factorial, what is 0 factorial? Does anyone remember what 0 factorial is? 1, exactly. 0 factorial is 1. 0 factorial is 1. Okay. Now, if we write a program for the factorials, one way of writing it is, okay, procedure is equal factorial, and it's accepting n, and n are non-negative integers. That's what they represent. Now, I want something that's being multiplied over and over again. So I'm going to call, I'm going to call that a product. And I'm going to give it an initial condition of 1. And I'm also going to get I and give that initial condition of I. Okay. Now, depending on what n is, that's how many times I'm going to multiply up to that number. So if n is 5, I'm going to do 1 times 2 times 3 times 4 times 5. So my idea is this, and here's my idea. Here's a product, I'll give it a box. And here's I, I'll give it a box. I starts at 1, oops, no. I starts at 1 and product starts at 1. I multiply these two, and in the end, I wanted to eventually get back, I needed to save it into one of these. Let's say I save it into product. 1 times 1 is 1. So that changes into 1. And let's say we don't, our n is 5. Now, I want to keep multiplying these two until I becomes 5. So in other words, what I'm doing is I'm going to increase I. So now let's say I is 2. 2 times 1, that's 2. And then I'm going to change that to a 2. So the product of I and product, I'm literally going to save it in product. And then I'm going to increase I to 3. Then 3 times 2 is 6. So if you notice what I'm doing is pretty much the same thing as I'm doing here. I'm multiplying 1 at a time. Does that make sense? Right? Now, that's if n is given some positive or some non-negative integer. But since it's a non-negative integer, that means n could be 0. So what will happen if I get 0? Well, if I get 0, I get 0 times 1, which is 0. So then this becomes 0. So now that becomes 0. And then I increase this by 1. Obviously, it surpasses our n, which is 0. So it doesn't work anymore. But in the end, it tells me that my prog will be 0. Well, that's not true. 0 factorial should be 1. So I'm going to have a condition that states when 0, make this happen. So what do you think I'm going to use? What pseudocode am I going to use? If, right. I'm going to use an if command. Oops. If n is equal to 0, then what I want you to do is this. Then I want you to return just 1. Right? If n is equal to 0, then I want you to return 1. Again, spit out back 1. Okay, sweet. But if it's not 0, so I'm going to use else, you're going to have to do a loop. And we know it's going to have to be a loop because we want I to keep incrementing until it hits n. So I'm going to say while I is less than or equal to n, do this. The product is equal to the product times I. To avoid any confusion, when you're using the times symbol, the multiplication symbol with pseudocode, just use an asterisk. So I know that that means times. You can use a period if you want, but make sure it's really, really bold. So I understand that you're meaning multiplication. Okay. But then obviously we got to increase I by 1. And then once you do all of that, return the product. Because the product in the end will represent our factorial. Does everyone see this pseudocode? Does everyone understand the pseudocode on what I'm writing? Yes, no? Oh, okay, you guys are so quiet. I sometimes don't know. And so I always keep my eye on the chat. I don't, on the syntax, yes. Remember that I want you to use the pseudocode that we're using in class. I don't want you to use any other type of pseudocode because, again, I don't know any other type of pseudocode. I'm trying to keep things fair in terms of what this class is using. So will I be strict on the syntax on the test? Yes, because, again, I want to keep everyone at the same level. The only thing that I say I will kind of accept, because I can see that, is for something like this. You can say I plus plus. I'm like, okay, I can see that. A lot of people are used to that, assuming you do code. That's the only one I will accept. Now, if you don't write the little things here, these colons, I'm not going to be strict on that. As long as you have equals and I'm like, okay, I know what you're saying. Good. Hopefully that answers your question. What about, yeah, I wouldn't, don't do I plus equals 1. I wouldn't do that one. Either do this one or this one. Okay. So this obviously is a pseudocode of doing a factorial. Now let's go back to the factorial because there's a reason why I'm doing this and you see what I mean. When we're doing the factorial, one option is to multiply all of these. Obviously, I can do it physically. 1 times 2 times 3 times 4 times 5, I can do it. You can use, I think there's pseudocode for 4. So if there's pseudocode for 4, then yeah, use a for loop. Yeah, and some of you will say, oh, can you do a for loop instead? Yeah, you could. So use a for. There's nothing wrong with that. You can use a for. But what you're seeing is that the computer can't really multiply all of those at once, like how I can do it in my head. But another way of looking at this factorial is that I'm taking these two, multiplying. Then I'm taking the next one, multiplying. Then I'm taking the next one, multiply. I get a result, take the next one, and multiply and get this. I'll say this again. What I'm doing is I'm taking these two, multiplying them. Then the result, I'm going to multiply with the next term, get a result. Multiply that with the next term, get a result. Multiply with the next term and get a result. So it kind of behaves like it kind of behaves recursively. Do you see what I'm saying? And that obviously, yeah, I start with 5 times 4, but I could start with 1 times 2. And then that gives me 2, 2 times 3. That gives me 6, 6 times 4. That's giving me 24. 24 times 5, that gives me 120. So it's like it is a recursive, it's like a recursive algorithm. Like it's recursively doing this to find the result at the very end. So what I'm trying to get at is another way of how to write this is using a recursive algorithm. Now, in pseudocode. So here's the recursive algorithm. Procedure, factorial, and obviously is a non-negative integer. If n is equal to 0, then return 1. Right? And we said that because if we run into the problem where the user typed in n, or our n is 0, if it tries to do this, it's not going to give us what we want. So we have this idea here. If this happens, if we have that condition, if this happens, give this back. And so I'm saying, if n happens, then return 1. So I'm saying the same thing. Else, do this. Return n times factorial of n minus 1. And my output is going to be n factorial. That's what the output is. So this pseudocode is very similar to the last one. The difference is that this is an example of the function calling itself. So this pseudocode is acting like a recursive function. Do you see what I'm saying? And we'll go through this code just so you can see it. But any questions on this? So again, we're writing now a recursive algorithm, but in pseudocode. That's pretty much what this section is about, recursive algorithms. That's why I wrote a recursive algorithm in the beginning. Okay, so let's test this out. How does this work? Well, suppose n is equal to 5. So let's go through this procedure. So factorial, and I'm given 5. So that's what it says here, given 5. Okay. If n is equal to 0, then return 1. Is n 0? No. N is not 0, so it doesn't do this statement here. Else, return, so then that means return 5 times factorial of n minus 1, which is now 4. Any questions so far? Okay, the problem is we have factorial 4. We don't know what this is, but this is calling itself. So that means I have to figure out what this is. So I'm going to write it out. Factorial 4. So that means I was here. I'm here. So now I go back to itself. N is now 4. Is n equal to 0? No. So I don't do this. Else, do this now. Return 4. Okay, so now I'm going to return 4 times factorial of 3. Okay, because it says n minus 1. So 4 times factorial of 3. However, I don't know what factorial of 3 is. So I'm here. And so I have to go call myself again to figure out what factorial 3 is. So now I have factorial of 3. I run through the program. N is not equal to 0, so don't do this. Else return. So I'm going to do else. Return. Okay, so I'm going to return something. 3 times factorial of 3 minus 1. But that's just simply 2. This is section 5.4. We're not doing section 5.3. Section 5.4. Okay, now 3 times factorial 2, but I don't know what factorial 2 is. And again, I'm here in the program in the pseudocode. So I'm going to call on myself again to figure out what factorial 2 is. So factorial of 2 is 2 is equal to 0? No, so don't do this. I'm going to do the else. Return, so I'm going to return 2 times factorial n minus 1. So return 2 times factorial n minus 1, which is just simply 1. But the problem is I don't know what factorial of 1 is. Okay. But again, I'm here in the program. So I'm going to call myself again. Is n equal to 0? Well, n is equal to 1, so no. So I'm not going to do this. I'm going to go else, return this. So I'm going to return. So I'm going to do factorial of 1. Going to figure that out. So I'm going to return 1 times factorial of 1 minus 1, which is 0. However, I don't know what factorial of 0 is. So I don't know what to return. So again, I have to figure out what factorial of 0 is. Okay. Now, if I do factorial 0, I'm calling myself again here. So factorial 0 is n is equal to 0. Well, the answer here is yes. Oh, here it is. Yes. So now, because that happens, return 1. So now I'm going to say return 1. Now I can work backwards. Notice that this is 1. So, okay, sweet. I know what this is now. So I go back to this. And this is just simply, so this finishes, this checks off. This is now 1. So I have 1 times 1, which is just simply 1. Sweet. So this checks off, this checks off. Okay, now I have factorial 2 says return 2 times factorial 1. I already know what factorial 1 is. It is 1. So this becomes 1. So now we have 2 times 1, which is 2. So that means factorial 2 is 2. So checks off. So I know now what factorial 2 is. Awesome. Check it off. So now I can answer this part. Factorial 2 is 2. Right? 3 times 2 is 6. Okay, so I now know what to return. Factorial 3 says to return this. Well, that is 6. Sweet. So I know what that factorial 3 is. So now I can do this. This changes to 6. And now I do 6 times 4, which is 24. So I'm done here. And now that means that factorial 4 is 24. Checks off. Now I know what factorial 4 is. So now I can do this here. Factorial 4 is 24. 24 times 5, that's 120. We're done with this. So now I know what factorial 5 is. That's 120. So my output, which is n factorial, this will state then, okay, 5 factorial is equal to 120 not factorial, just 120. And that's how this recursive algorithm works. So you can rewrite the same program, but you can do a recursive algorithm. And what I mean by recursive algorithm is where it calls upon itself. It's pretty much a problem that can be solved using itself to solve it. That's essentially what the basic idea of a recursive algorithm is in pseudocode. It's something that can solve in terms of itself. And in this example, the factorial is a perfect example of where it can solve. You use itself to solve itself. Does that make sense? Any questions on that? Any questions? Can you change the condition if n is equal to 1 to if n is equal to 1? Yes, you could. You could change the condition whatever you want. The important thing, though, when writing these recursive algorithms is you want to be able to stop. Notice that this condition helped us stop. Because assume that that condition wasn't even there, or it was a condition that you can never reach. Then this could have theoretically gone forever. Do you see what I mean? So as long as you have a condition, yeah, you can say if n is equal to 1, and that most likely meant you would have probably stopped here. Well, actually, you still would have done this, but you will have to probably change in such a way where the condition can be, okay, if n is equal to 1, do this. But this condition is very important. This is known as your base case. This is known as your base case. This is needed to stop the recursive function. This is needed to stop the recursive function, because without that, the whole point of this here, when you look at this very carefully, when we're doing it, the whole point of this was to eventually reach this condition. Because if it didn't reach that condition, we would have kept going and going and going. So this would have kept going on forever, and that condition would have never reached, which means your recursive function algorithm would have kept on going in an infinite loop. Does that make sense? Any questions on that? Any questions? And again, it helps to write it out like this, because then you can see, oh, okay, this, I can see what it's doing. No? Okay. Again, and I'll write this out here. An algorithm definition, and I'll use an algorithm is called recursive if it solves a problem by reducing it to an instance of the same problem with smaller inputs or input. And that's actually what we did. So an algorithm is called recursive if it solves a problem by reducing it to an instance of the same problem with smaller inputs. So what you saw, notice with the factorial, that's exactly what we did. We kept reducing the value of n. But in the end, it was still the same problem. We're still multiplying two numbers. But we're using itself, we're reducing the numbers to smaller inputs, such as this, to solve itself. And that's what you call a recursive algorithm. Or in other words, it's a program that uses itself to solve itself. That's another way of looking at it. It's a program that uses its own terms to solve itself. It can solve in terms of itself. Okay, let's do another example. Does everyone have this down? Yes, no? Almost, okay. Let me scroll up slowly then. Let's write a recursive algorithm for something like this. Give a recursive algorithm for computing the GCD of A comma B, where A and B are greater than or equal to 0, A and B are any integer, and A is less than B. So give a recursive algorithm for computing the GCD of A comma B, where A and B are both positive integers, or non-negative integers, I should say, because that's what I'm saying here. They're both non-negative integers, but A must be less than B. Okay, so and I want to create a recursive algorithm. So I want to write pseudocode where a function calls upon itself to solve it. Now, how do we do that? Well, first you have to understand how this works. The only way we're going to understand how this works is by doing a couple of examples. Because by seeing that, then you're like, oh, okay, I can see a pattern and I can see how I can write this algorithm. Well, that's what I would do because it will help me out. So the GCD, suppose we have the GCD of 5 comma 8. We already know what the GCD is. Most of us probably already know what the GCD of this is. But how would we find it if we didn't know how to do that? Well, one way that we can do that seems to be in a recursive form way, where it uses itself to solve it. It uses itself to solve, is pretty much the Euclidean algorithm. Remember? The Euclidean algorithm, which is something of the form that says 8 is equal to 5 times something plus some remainder. So 5 times 1 plus remainder of 3. But this doesn't, I still have to keep going. Okay, so then I get 5, put it here, and then I get 3, put it here. 3 times 1 plus what remainder gives me 5. Well, 3 times 1 plus the remainder of 2 will give me 5. I keep going because this doesn't tell me my GCD still? Okay, 2 times what plus what remainder gives me 3? Or 2 times 1 plus 1. Okay, I keep going. Here's my 2. Here's my 1. So 1 times what plus what remainder gives me 2? Or 1 times 2, what a remainder of 0. And this is where I stop, usually. Why is that where I stop? Because now I know what my GCD is. And what is my GCD? What is my GCD? 1. Exactly. My GCD is this number here. So this is equal to 1. Okay. So I have a general idea of like, okay, I see how I can write this program where it calls upon itself to do this. It seems like it depends heavily on the remainder though, because that's what we're doing. We're eventually getting the remainder and taking eventually the GCD of doing the Euclidean algorithm of these two, then take the remainder, doing the Euclidean of these two, take the remainder, and again, and so on and so on. But in computer code, what tells us a remainder? Or what spits out a remainder? What code spits out a remainder? Or what function spits out a remainder? Modulo, exactly. So this could be the same thing as, well, actually not that one, this one. This is the same thing as saying 3 is congruent to 8 mod 5. All right. That's the same thing as saying that. How do I know that? Because remember that when you have something of the form A is congruent to B mod M, this states M divides the difference of A and B. So that's what we're doing here. I take the difference of 8 and 3, and then I divide it by 5. And that will give me obviously 1. So that's what I'm doing here. I'm doing 5 divides the difference of 8 and 3. So I'll write it like that so you guys don't get confused. 5 divides the difference of 8 and 3. Well, in this case, it'll be 3 minus 8, but it's still the same idea. Okay, let's keep going. This is the same thing as saying, in this scenario, that's going to be 2 is congruent to 3 mod 5. Oops, sorry, no, 5 mod 3. All right, then I go here. This is the same thing as saying 1 is congruent to 3 mod 2. Oops. And then this one's the same thing as saying the last one. 0 congruent to 2 mod 1. Any questions for? Any questions? So I see a pattern now. I see a pattern. I'm starting to see a pattern, and it's going to help me write out this recursive algorithm. If I change this to simply A and B, so if I change the 5 to an A and the B to a, and the 8 to a B, because I want it to work for any A and for any B that fall in these conditions, I can see a pattern. Okay. Technically, this is the same thing as saying the GCD of 5, 8. This is the same thing as saying the GCD of 3, 5. This is the same thing as saying the GCD of 2 comma 3. And this is same thing as saying the GCD of 1 comma 2. So this is my A and this is my B. But then when it went to the next one, notice that my A went here and my B went here. Actually, no, my B didn't go anywhere. What does this 3 represent now? What does that 3 represent? It's an A, but what did it represent before? What did it represent before? What did that 3 represent before? Let's see if this helps. Notice that this 3 became here, went there, but then we got a 2 here. Right. Though the 3 and the 2 here represent the remainder. So this is the remainder. So I'll call that R. But we already know how remainder is found. Our remainder is 8, was given by 8 mod 5. So this is the same thing as just saying A mod 5. Then the 2 is the same thing as saying 5 mod 3. Right? And then the 2 changed to here. But R1 is the same thing as saying 3 mod 2. So if we write out a program where we're interested in GCD, we know that if we're doing this recursively, the number that keeps getting smaller and smaller is this, the number that's in this position here. And that number seems to be always the remainder of the last one. Do you see what I'm trying to get at? So just for a basic idea, I'm going to write it out like this, just for right now. The GCD of what it seems to be like B mod A, comma, A. If I keep returning this, and I'm writing it piece by piece, if I keep returning this, it's going to keep getting smaller and smaller and smaller. So return the GCD of B mod A, comma, A. Why is A here? Because it seems that A keeps going to this position when we're doing this process. But this A here gets changed to the remainder. Does that make sense so far? So that means if I want to write so far like the skeleton of this program, the pseudocode, I'm going to say, okay, here's my procedure. It's going to be a GCD. And I want to say GCD because I want this to call on itself. So that's why I'm going to say GCD of A, comma, B. So this GCD or this function is going to take 2 inputs, both non-negative. And A is less than B. Eventually, I'm going to have, and I'm just going to write base case right here because I don't know what my base case is yet. But once the base case is done, it's going to be else. And now I'm going to say return the GCD of B mod A, comma A. Does that make sense so far? So this is just a rough skeleton. Obviously, we're not done yet because I don't know what my base case is. But I can see the recursive already, the recursion, where this number keeps reducing. Now, I want a base case because then if I don't have a base case, this is just going to keep on going forever. It's going to run an infinite loop. So I want a base case. What will be a good base case here? And remember that when it's going back to itself, it's calling itself here. This is my new A. And this is my B when it calls itself again. So even though this does represent the remainder, when it calls itself again, this is my new A, and this here is my new B. And then it runs through the thing again. So if I want this to stop, I need a good base case. What do you think my base case would be here? Or what's a possibility? Any ideas? Well, if you're having trouble, one way of thinking about it is like, okay, I'm doing this, and I realize when we hit 1, we stopped. And since this is technically my new A, every time I go back into the program itself, I can say, as just a possibility, if A is equal to 0, then it's going to return something. And we'll talk about that something in a sec, but if, not 0, sorry. If A is equal to 1, then I want you to stop. Right? That seems like a not bad idea. If A is equal to 1, I want you to stop. Why? Because that's where we traditionally stop. So if A is equal to 1, I want you to stop. You're going to return something, and I'll specify what that something is in a sec. But we're going to return something, right? But the thing is, does this always work? We tried it with two numbers that don't have anything in common. And that gave us a GCD of 1. But does it always happen that our numbers reduce to 1? This one here always reduces to 1 if they do have something in common. Well, in order to figure that out, let's do another example. The GCD of where are two numbers that have something in common, and you want to keep it small. You don't want to do something big because then honestly it's just going to take longer time. What's a good two numbers that have something in common? Any two numbers that have a factor in common? No? You guys can't think of any? Okay. How about 24 and 32? So I'm just saying that so far our base case is if A becomes 1, I want to stop, because that's what it looks like with this example. When A became 1, we stopped. But does that always happen? So I'm going to pick two numbers that do have something in common, and let's see if that works. So 32 is equal to 24 times what plus what remainder? We'll be at 1 plus 8. We take the 24 is equal to, and then we take the 8. 8 times what gives me 24? plus what remainder? 8 times 3 plus a remainder 0. Now we stop. However, we look at this, we notice that yes, we stop here. So if we rewrite using the GCD, this is the GCD of 24 comma 32, sorry, and this is the GCD of 8 comma 24, right? However, notice that the 24 became an 8, and that's where we stopped. So if we run this program, will this ever stop if we input something like this? If this is our base case. If we run this program using these numbers, will this ever stop? No, it's going to keep going on forever, right? It's going to run an infinite loop. Why? Because we say let A be 1, but in this scenario, A is not 1. So this is not a good base case because we run into a problem of an infinite loop. So that means, what can I do? Well, let's go back to this thing here. What if I take it one more step? What if I did one more recursion? If I did one more recursion, then this goes here, and this goes here. 0 times what gives me, and then when I add it gives me 1. So 0 times 1 is 0 plus 1. So this is the same thing as saying the GCD of 0 comma 1. And this is the same thing as saying 1 is congruent to 1 mod 0. Can everyone hear me now?
Yeah, we can hear you.
Yeah, so what ended up happening is my laptop ran out of battery. It's pretty ironic. Okay. Now, sorry. Now let's continue with this. And then I'll give you guys a small break. Okay. So it knows that if I do one more step, I get this. I'm assuming, does the same thing happen when they do have something in common? Well, let's find out. I'm going to take 8 is equal to 0 times what plus what will give me 8? Well, 0 times, I can say 1, and then I'm going to have to add a remainder of 8, right? So this is the same thing as saying the GCD of 0 comma 8. And this is where it gets interesting. They both do have 0 for A, which means perfect. I can change this back. I can change this A to a 0. Because under both conditions, when they have something in common and when they don't have something in common, if I just take it one more step with the Euclidean algorithm, then I end up getting 0 in the A position for the GCD. But not only that, if I look at my B position for this GCD, does this represent? So what does this one represent for this problem? What does this one represent? For this problem here? Or if it helps better, because you probably see it better with this one, what does this 8 represent for this one here? What does this 8 represent for this problem here? Right, the solution. So that means that our B position for our GCD seems to be the solution to the problem. So that means now I can say something here. If A is equal to 0, I want you to stop, but then I want you to return the value of B. And now I can write the pseudocode properly. It will be procedure GCD of A comma B, where they're both non-negative integers. And A is less than B. Then what I want you to do is if A is equal to 0, stop. But return B. Else, if A does not equal 0, I want you to keep continuing finding the GCD. I want you to return the GCD of B mod A comma A. And in the end, your output's going to be the GCD of A and B. And that's how you write a recursive algorithm. Does this make sense? If it doesn't, say something. I know this can be a little confusing, but any questions on this? And then you can test it out. You can literally test it out yourselves. We can test this out. We can say, okay, let's suppose we have the GCD of A comma 5. Oops, 5 comma 8, because A has to be less than B. Let's run the algorithm. Is A is equal to 0? No. Then else do this. Return the GCD of 8 mod 5 comma 5. Okay. The problem is I don't know what this is. So that means I'm going to go back into here. So now I have the GCD of 8 mod 5. But 8 mod 5 is 3, comma 5. The 5 still stays the same. But 8 mod 5 is 3. Okay, A is not 0, so do this again. So return the GCD of 3 mod, oops, sorry, not 3, 5 mod 3, comma 3. But again, I don't know what this is. This entire thing is. So I'm going to go back into the function itself and then do GCD of 5 mod 3. But what's the GCD of 5? What is 5 mod 3? That is just simply 2. So 2 mod, so now I get 2 comma 3. So A is not 0. So I'm going to do this instead. Return the GCD of 3 mod 2, comma 2. Okay. Again, I don't know what this is. So I'm going to have to go back into the function. So I'm going to do the GCD of 3 mod 2. But I know what 3 mod 2 is. That's simply 1, comma 2. Right? So is this 0? No, it's not. So keep going. So do this. So I do return the GCD of 2 mod 1, comma 1. Right? Okay. Again, I don't know what this is. So I go back into the loop. So GCD, I mean into the function, 2 mod 1, oh, I know what that is, 0, comma 1. Now notice A here is 0 now. So is A 0? Yes, so return B. So return 1. And 1, in this case, our B is 1, so that's why I'm returning 1. Okay, so now I can go backwards. So I'm done with this, I'm done with this. So now, this is the same thing as saying the GCD of 0, comma 1, but I already know what that is, that's 1. So this entire thing becomes 1, so I'm done with this. So now I know that the GCD of 1, comma 2 is 1, which means that this is the same thing as saying this. So now that becomes 1, so I'm done with this step. Now the GCD of 2, comma 3 becomes 1, so I'm done with that. But the GCD of 2, comma 3 was the same thing as saying the GCD of 5 mod 3, comma 3. So this becomes a 1. Done with that. So that means that the GCD of 3, comma 5 is 1. And then I go back to this. The GCD of 8 mod 5, comma 5. We know that's the same thing as saying the GCD of 3, comma 5. So now this became a 1. So return 1. So that means the GCD of 5, comma 8 is 1. So my GCD of 5, comma 8 is equal to 1. And voila. Any questions? Any questions? No? Okay, I'm assuming some of you need like a break. So take a 5-minute break and then we'll continue. If you have questions, let me know. Is this top-down recursion? I don't know if that's the name that they're giving it in computer science. I'm assuming that's a computer science term. They call it in the book recursive algorithm. So I'm just keeping with that. But I think I can see why it could be called top-down recursion. But the way I look at it is you're going in one direction, you're going down first, and then you're going up first. So I can see how you can call it top-down or down top. Mm-hmm. All right, can everyone hear me now? And this time I have my laptop connected, so shouldn't die on me. Or I don't want to say die because it doesn't really die. It just runs out of battery. Okay, so. Okay, let's do one more example of this. Let's do one more example. Let me write it out. Give a recursive algorithm for finding the maximum of a finite set of integers, making use of the fact that the maximum of n integers is the larger of give a recursive algorithm for finding the maximum, sorry. I should have said maximum here. Thank you. The larger integer in the list and the maximum of the first n minus 1 integers in the list. So give a recursive algorithm for finding a maximum of a finite set of integers, making use of the fact that the maximum of n integers is a larger integer in the list and the maximum of first n minus 1 integers in the list. Well, making the fact that the maximum of n integers is the larger, that's what it doesn't make sense. I miss the complete word here, is the larger of the last, there it is, integer in the list. That makes more sense. Sorry, that's my fault. That should clear it up. Okay, give a recursive algorithm for finding the maximum of a finite set of integers, making use of the fact that the maximum of n integers is the larger of the last integer in the list and the maximum of the first n minus 1 integers in the list. Okay, so that's, if you're trying to interpret that, this is what it's saying. Suppose we have a list of integers. Okay, here's a list. It's a finite set. This is a sub 1, a sub 2, a sub 3, a sub 4, a sub 5. I'm gonna need more space. Blah, 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 blah. This here is a sub n minus 2, a sub n minus 1, and this is a sub n. Okay, so what is this saying? Give a recursive algorithm for finding the maximum of a finite set of integers, making use of the fact that the maximum of n integers is the larger of the last integer in the list and the maximum of the first n minus 1 integers in the list. So let me highlight something. Making the use of the fact that the maximum of n integers is the larger of the last integer in the list and the maximum of the first n minus 1 integers in the list. So what is that saying? So what it's saying is this. I'm going to take this one out. So let's take it out. So, or in other words, another way to think about it is break it apart. So here's a sub 1, a sub 2, a sub 3, blah, 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 a sub n minus 1, no, n sub n minus 2, and a sub n minus 1. And then here's this one on its own, a sub n. So it's completely on its own. It's like a wee on its own. Okay. So what's saying is this. The larger of the last integer, so is the larger of the last integer in the list. So I want to find the maximum of these first, and then eventually compare it to this one here. That's what this is saying. I want to find the maximum of this one, and then eventually compare it to this one here. Does that make sense? Any questions? No? Okay. So, how do we do that? Well, we want a recursive algorithm as well. We want it to be a recursive algorithm. By definition of a recursive algorithm, it's a problem that can solve itself. Okay. Or it's a program that can use itself to solve itself. Or another way of thinking about it, as what we were seeing here before, we can reduce it to an instance of the same problem with smaller inputs. So like how we were doing here, we were reducing to a problem of smaller inputs. Same thing with this GCD example. We were reducing it to a problem of smaller inputs. So what I'm trying to do here then, if I have a list, I eventually want to reduce this list into smaller inputs. And what I mean by that is, let's say I have n minus 1 on this list. Then what I want to do is I want to reduce this to a list of n minus 2. And then I want to reduce it to a list of n minus 3. And so on and so on. Eventually reduce it to a list of a sub 3. So pretty much just 3 terms. Then reduce it to a list of 2 terms. And eventually reduce it to a list of 1 single term. Because once we reach a 1 single term, I can tell it to stop. And then once we tell it to stop, it's going to go back the other way around, meaning it's slowly going to increase by 1. Which means that if it slowly increases by 1, I can have these two compare each other, get the maximum. Then whatever I get these two, compare the maximum. Then whatever I get the next two, compare the maximum, and so on and so on. Eventually taking up this entire thing to eventually compare it to this. Does that logic make sense? Any questions? And I'll repeat myself what I said. In the end, I want this n-1 list to get smaller and smaller and smaller and smaller. Because if it's a recursive algorithm, I eventually want it to stop. And the whole point of the recursive algorithm, or algorithms called recursive, is I can get it down to a problem where it only depends on smaller inputs to help it solve it. So if I'm trying to get this into smaller inputs, that means I don't want n-1 inputs. I want smaller inputs, which n-2, then n-3. Eventually, I only want 5 terms. Then I only want 4 terms. Then I only want 3 terms. Then I only want 2 terms. Eventually, I only want 1 single term. So I'm trying to reduce it to the smallest it could possibly be. Does that clear it up for you? Okay, so let's write this out. So my procedure is pretty much the max. I'm trying to find the max, and what's going to be inputted are a sub n integers. Or in other words, a list of integers. Another way you could think about it is that this is the number of terms it's going to have. So n terms, and that's another way of thinking about it. Now, I need to create a base case. If a sub 1, or no, I shouldn't say, if n is equal to 1, then return a sub 1. Now, why am I saying that? This is why I'm saying this. In the end, I realize, again, I want to get this into smaller inputs. So eventually, I want to get it to a sub 1, which means this is going to be the only term in my list. So if n is equal to 1, that means I want 1 single term only. And in 1 single term, I want you to return that value, whatever that value is. And that value is going to be a sub 1. Now, eventually it's going to go backwards, which means it's slowly going to increase the size of 1. So that means as soon as I grab this one, it's going to work backwards. It's going to go back to a size of 2. So I want to compare that one to this one. Get the max of these two. Once you find the max of these two, and then again, it's going to increase by 1 because now I'm going backwards. Then compare the max of these two and a sub 3, and so on and so on. If you're wondering, well, why are we going backwards? Well, remember that when we were doing this pseudocode for the GCD and even for the factorial, we went in this direction, trying to get to small inputs. And then once we have our base case, we went back up. So my idea is to reduce these by 1 each time. Eventually, I'm going to have to increase it by 1 each time. Does that make sense? Yes? No? Okay. So if it's not a list of just a single term, then I want you to go back into that list, but this time reduce it by 1. Okay, I want you to find the max of that and keep reducing it by 1. And if once you know what that max is, save it into a variable. Let's call it M. Okay. So let's see how this just works right now. Obviously, it's not fully done. It's really not fully done, but let's see how this works. So suppose we have, here's my program, max. Let's say we have 6 terms in there. Okay, we have 6 terms. A sub 1, A sub 2, A sub 3, A sub 4, A sub 5, A sub 6. And I'm starting with A sub 1. I know majority of programs start with A sub 0, A not. But then for this example, let's just keep it with 1, just to keep it simple, okay? So A sub 1, A sub 2, blah, blah, blah. So this has 6 terms. Is n is equal to 1? No, it's not. So else, do this. So I'm going to do the max. So do this and then return something. I don't know what I'm going to return, so I'm just going to say this, and then I'm just going to say this. Okay. M is going to equal to reduce it by 1, max of 5, but then it's going to return eventually something. I don't know what that is, but we'll figure that part out. Okay, max is equal to 5 and save it into M. Or if you don't see this return, I'll just take it off for right now. Okay, max is equal to 5, so save that into M. But I don't know what max 5 is now. So that means I'm going to go back into my sequence. So max 5, I'm going to give myself some space, and you'll see why later on. Okay, max 5 is 5 equal to 1, meaning is it a single term? No, it has 5 terms. Okay, so skip this, do this. So I'm going to do max, reduce it by 1 more, so that's 4 now, and then save that into M. But again, I don't know what max 4 is. So I'm going to go back to my sequence. So I'm going to say max of 4 is n is equal to 1. No, I have 4 terms. I don't have 1. So that means skip this, go else. So I'm going to do max again, but this time 3. I don't know what max 3 is. I'm running out of space, so I'm going to write it on the side. So I'm going to write max 3, because I have to go back into myself. Is 3 1? No, it's not. So do this. So I'm going to have max 2. Again, I don't know what max 2 is, so I'm going to keep going. And now I'm going to have max 1. Awesome. So the max of 1. Well, if n is equal to 1, yes. Then you need to return a sub 1. Okay, so we stop here because this tells us to stop. So we stop. We have a good base case. But now I have to return. So let's say I return. So this is a sub 1. Now, if it helps you and you need a list to visualize this, let's create a list. Here's my stack. 1, 2, 3, 4, 5. 6. So a sub 1, a sub 2, a sub 3, a sub 4. That's not a sub 4. This is a sub 4. A sub 5, a sub 6. Okay. Now let's give it these numbers. 2, 4, 3, 1, 22, and 3. So I'm going to return a sub 1, which is 2, according to my example here. Okay, so max of 1 is, oh wait, I skipped max 2. I didn't even do max 1. Oops, my bad. So I can't even do this return yet. My bad, my bad, my bad. Sure, some of you guys are screaming at me. Like, no, you're not done yet. Now I can do max 1. Sorry. And now I return a sub 1. Okay. So here we go. A sub 1 is 2. So max of 1 is 2. So this becomes a 2. Okay. That means that this is 2. This is why I'm saying save this number into something, another variable, 2. However, notice what you're technically saying here. Max 2. How many terms do you have here? How many terms do you have in here? How many terms? Not 6. How many terms do you have here? 2 terms. You only have 2 terms, a sub 1 and a sub 2. Those are the only terms you have here. Sorry, you only have 2 terms. So if you already know that a sub 1 is 2 from the previous thing, because that's what you're getting, this is where you stop, you want to compare these two, right? But you're not comparing them anywhere because you're not saying that anywhere in your pseudocode. So we should say that. We should say, okay, if once I get it down to a specific number, I want you to do the following. If M is greater than a sub n, then return M. But if it's not, return a sub n. Now, what do I mean by a sub n? Well, what I'm saying here is this. If a sub 1 is bigger than a sub 2, return a sub 1. However, if that's not the case, then I want you to return a sub n. And in the list of 2 terms, a sub n is a sub 2. Does that make sense? Does that make sense? I'll repeat it again. So I'm saying is this. Once you have that term, save it into some variable. Okay? A sub 1 is 2, and I'm saving it into variable m. When we're here at max 2, we have 2 terms. I want to compare these two. So I'm saying is compare a sub 1 with a sub 2. And a sub n is my n in a list of 2 terms. So if this is larger than this, return a sub 1, which is 2. But if it's not, then return a sub 2, which is 4. So that's what I'm going to write here. Return, well, what are we returning here? Well, is a sub 1 larger than a sub 2? No. So we return, so we don't do this because this is not true. So we return a sub n. And in a list of two terms, a sub n is a sub 2, which is the last term. So this is a sub 2, which is equal to 4. So I'm done with this, I'm done with this, and I'm done with that. Now I know what max 2 is. So max of 2 is 4, which is a sub 2. Okay. Now, this is within max of 3, which means now I'm looking at these three terms here. So I'm looking at these three terms. But I'm not looking at these two anymore because I already know what the max of these two are. It is 4. So essentially, all I'm really comparing are this one and this one. Okay, so if m, which is 4, is greater than a sub n, in this case, in a list of 3 terms, a sub n is a sub 3, then return a sub 2. So in this example, is 4 greater than what's in a sub 3? Yes. So I'm going to say return a sub 2, which is 3. No, sorry, not 3, 4. So we're done, and we know what max of 3 is. Max of 3 is 4. And now we go to this thing here. Max of 3 is 4. But this is within a list of 4 terms. So now I'm looking at these 4 terms. Okay, looking at these 4 terms, I already compared the first 3, so I don't have to worry about that. All I have to compare is now a sub 2 with a sub 4. So is 4 greater than what's in a sub 4? Well, let's find out. 4 is greater than 1. So then I want you to keep returning a sub 4, I want you to return m, which m was 4. So I'm going to say return 4. So we're done here, here, and now max of 4 is 4. So now this changes to a 4, and that's what m is now. But this is within a list of 5 terms. So now these terms here, these 5 terms here. Okay. 4. So I'm not really comparing all of these 5. What I'm actually just comparing is this 4 and whatever's in a sub 5. So I'm really comparing these two. Is 4 greater than whatever's in a sub 5? So is 4 greater than 22? No, it's not. So this is false. So we do else, return a sub n. Well, a sub n is a sub 5. So I'm going to return a sub 5, which is 22. So that means max of 5 is this 22. So now I'm going here. Max of 5 is 22. So m gets saved with 22. But I'm within a list of 6 terms now. And that's what that's exactly what I wanted. I wanted to compare the maximum of the first n minus 1 integers with the max of with the number of a sub n, which in this case is the last term. So I'm comparing 22 with a sub 6. So is 22 greater than a sub 6? Well, a sub 6 is 3. 22 is greater than a sub 3. 22 is greater than 3, sorry. So return 22. So return 22. So I'm done with this. I'm done with this. So max of 6 is 22. So hence, it is going to return the maximum number. within this list, and that is 22. So this does work. Any questions on that? Any questions? Okay, the difficult part, and honestly, I can see it being difficult, is going to create this recursive algorithm. But you should always check it, because you want to make sure you don't run in an infinite loop. And when you're checking it, make sure you organize it. Don't just write it everywhere, because obviously I'm going to look at this. Yeah, I can see what you're saying. It's a little tedious. I can see that. Now, I know some people have told me, oh, because this is actually, not some people. I talked to people about the recursive algorithms in computer science, and for me, I'm assuming this will take a lot of memory, because technically when you're calling it, you're creating a new space, or you're allocating more memory to create that, if I'm correct about that assumption. So you have to be careful with these. If you don't have a good base case, and that's the most important part, you're probably just going to go on forever. Yeah, but the whole section is about recursion, so that's why. Yeah, I can see this doing with a loop instead, but because the entire section is about recursion, I'm showing you recursion. Okay, so this ends section 5.4. I don't really want to start 5.5 because I only have like about 15 minutes, and I don't think that's, I'm sure I can do it in 15 minutes, but I don't want to push it. So instead, what I'm going to do is now I'm going to talk about your exams, because I'm sure everyone noticed that I uploaded exams. Well, I'm hoping you guys know this. So I uploaded your exams and your quizzes, and hopefully you look at your exams and you look at my comments. Make sure you read those comments. Now, if you realize number 3 is not graded. Number 3 is not graded on any of your exams. And the reason for that is when I saw it, I was like, I didn't word it correctly. So instead, I just took it off. And if you see a +2 on your exam, which everyone should see that, is because I just gave everyone 2 extra credit points for it. So everyone got a bonus 2 points. Okay. So that's what happened with number 3. So that's why it's not graded, because it was miswritten. And so I just took it off and I gave everyone 2 points extra credit just to make it work. Now, because we have time, and not enough time, but if you want to talk about your exams, not right now with everyone here, because that's a whole personal thing, you can. We have a couple minutes, and then I can just create some breakout rooms. I'll create 27, 28 breakout rooms. And you just choose a room, and then I'll try and come into that room if I see someone in that room and talk to you about your exam if you want to. But other than that, if you have questions on your exam, see me during the office hours, because that way I can understand what you're asking, and then you can hear me what I'm saying. There's no confusion, in other words. So if you're up for that, I'm going to open up the rooms. If you're not, you're more than welcome